All right, so this is a re-upload or a re-record for the week 21 fluid mechanics because the video quality for that video, sorry, the audio quality for that recording or that session was not good as I was in the train that time. So we are just quickly going to see all these questions. I am not going to go through all the explanations, whatever I tried in that session. But still we'll see how we solve the questions. Okay, so question number one, GATE 2008, question number 53. The flow of water, mass density 1000 kg per meter cube and kinematic viscosity 10 power minus 6 meter square per second in a commercial pipe having equivalent roughness Ks of 0.12 mm yields an average shear stress at the pipe boundary of 600 Newton per meter square. The value of Ks by delta dash being the thickness of laminar sublayer for this pipe is, so options are 0.25, 0.5, 6 and 8.0. Now, we are asked Ks by delta dash and we are already given Ks 0.12 mm or 1.2 into 10 power minus 4 meters. So the only thing we have to do is find the delta dash, that is the thickness of laminar sublayer. So how do we go about doing this? There are few things that we need to know before solving this question. Basically, Reynolds number, that is Vd by mu, where mu is the kinematic viscosity, v is the velocity, d is the diameter of the pipe, and the shear stress at the boundary of the pipe, that is given as mu du by dy, right? Where this is the viscosity, mu and mu. So see this basically mu by rho is given as your mu. I may be pronouncing them wrong, but you remember that one is kinematic viscosity, one is dynamic viscosity. Okay. Now for commercial pipes, du by dy can also be written as u by y. Okay. So these two expressions are going to be used, and we will have the expression for friction velocity. We will derive the expression for friction velocity, that is V star. Probably you are already familiar with this derivation, but I am just letting you know that these two are the things that are used. Okay, just a minute. Tau is equal to mu u by r. So this V star, the friction velocity, is given as tau naught divided by rho root under. And we have a quantity that is variable for different depth, that is V star y divided by mu. And this quantity, when you put y is equal to the thickness of laminar sublayer, is equal to a constant number, that is 11.6. So you have to remember this. This is the most important formula or the assumption in this question. And this probably you would have seen it a lot of times already in the fluid mechanics, because we come across this particular equation a lot of times. So these two are the important formulas that you have to remember. Now using this formula, we'll get the V star. So V star is tau naught divided by rho. Tau naught is the friction that is experienced at the wall of the pipe. It is given as 600 Newton per meter square. We have 600, and then we have our rho, that is the density of water, that is 1000 kg per meter cube. So the friction velocity is 0.6 meters per second. Okay. Then we can use this friction velocity calculated here to calculate the value of delta dash, that is the thickness of laminar sublayer. So root under 0.6 delta dash divided by our kinematic viscosity, that is 10 power minus 6. 10 power minus 6 is equal to 11.6. So the delta dash value computed based on this is going to be 1.49. We can say 1.5 into 10 power minus 5 meters. This is the thickness for laminar sublayer. Now when you know this, you can easily calculate the value of K by delta dash. So you have 0.12, or let's just keep everything in meters. 1.2 into 10 power minus 4 divided by 1.5 into 10 power minus 5. So 12 divided by 1.5. This is basically 8. So the answer for this question is option D, is 8. Okay, question number 2. So the question number 2 and 3 are basically two part question, and the given statement for this question is going to be same, but just for completeness I have included this in both the questions. Okay, so the question is GATE 2008 question number 82. An automobile with a projected area of 2.6 meter square is running on a road with a speed of 120 km per hour. The mass density and the kinematic viscosity of air are 1.2 kg per meter cube and 1.5 into 10 power minus 5 meter square per second respectively. The drag coefficient is 0.3. The drag force on the automobile is. So this is a very simple question. You just simply need to know the formula for the drag force, that is CD rho A V square by 2. You should be familiar with this formula because this is used in lot of our uh, fluid movement kind of fluid kinematics kind of studies. So let's see what are all the values. CD is the drag coefficient that is given to us. Rho is going to be the density of the fluid in which this motion is occurring. So in this case, it is going to be air. So we are given the density of air. We don't have to assume. And A is going to be the projected area. So if you have a rectangle cube, let's say, and you are moving this cube in such a way that one face of the cube is experiencing the wind on the surface, then this area of that face is going to be that area. If you have a sphere, then the maximum circle area of that sphere is going to be the projected area. So that is also given to us directly for the car. Velocity is the rate with which the object is flowing or object is falling. That is also given to us 120 kilometer per hour. So basically, we can calculate the FD using this formula. So 0.3 into rho 1.2 into area 2.6 into velocity square. So velocity is given as 120 kilometer per hour. We just multiply it by the conversion factor that I have told you earlier. So you want to convert from kilometer per hour to meter per second, you have to multiply by 5 by 18. Right, so you have 120 into 5 by 18. So the velocity is going to be 33.33 meter per second. So let's just substitute the velocity here and we'll get the value of FD. 519.89 Newton or 520 Newton. So option D is the correct answer. In this case, this drag force formula was the important. Coming to the last question, GATE 2008, question number 83. An automobile with projected area of 2.6 meter square is running on a road with a speed of 120 kilometer per hour. So this is basically the same theory as our question, and only uh, thing that is being asked is what is the metric horsepower required to overcome the drag force? So what is the horsepower that the car should have so that we can uh, maintain this kind of velocity even after experiencing the drag force of 520 kilonewton, sorry, 520 newton. So what is the formula for power? Formula for power is force into velocity, right? And what is the velocity? We calculated earlier velocity 33.33 meter per second. So we have to maintain this velocity while experiencing this force. So we have to actually generate this much force. So what is the power required for that? Force into velocity. 520 into 33.33. That is 17331.6. This is basically Newton meter per second, or you can say watt, right? But they are asking the power in horsepower. So we need to know the conversion unit for watt to horsepower. So how much watt is 1 horsepower? 1 horsepower is 735.5 horsepower. Sorry, 1 horsepower is 735.5 watt. So if you want to get this power in terms of horsepower, we just divide it, and answer is going to be 23.56 horsepower. So what is the closest option here we have? That is option C, 23.23. That is the correct option. So here what we needed to remember? We needed to remember that a conversion factor from 1 horsepower to the watt, equivalent watt. So, so you can see that these questions are pretty simple questions, and I purposefully took these simple questions because I didn't want to create. I knew that there was going to be some kind of problem in the connection when I'm traveling, so I didn't want to spend some precious questions. Those other questions, if there are other questions, very important questions, they can be taken by some other NPTEL team member. But these are the questions that we discussed on that day. And I hope this time recording is suitable enough for everyone to understand. All, that's all.